Yep, recording has been started.
Yeah.
Let's start the presentation 5. So we are from the group 24 and we have a team members Nida, Karthik and Pavan. So today we are going to discuss on the something related to mastering the game of Go with the deep nuclear networks and that research. So these nuclear search to minimize the search trees, effective depth and breadth, and it the value network evaluates the places and a policy network sample actions, and it directly we are going to start directly training on a supervised learning policy network on a human movements. Following the next training action will be on the reinforcement learning policy network to enhance the supervised policy network by maximizing the ultimate outcome of the self-play games. And finally, we are going to train on the value network that predicts the winner of the game, in which the reinforcement learning policy network computes with itself. By this, the Monte Carlo tree search and software AlphaGo effectively mix both the networks like policy network as well as the value network. And the next slide deals with the supervised learning of the policy network. So this is one of the first step of the training pipeline, which the working of this learning policy is predicting the expert moves in the game of Go, and it contains the layering with the weights as well as the rectifier non-linearities alternatives in the supervised learning policies, as well as it links with the softmax layer outcomes and the probability distribution over all legal moves, as well as the input to the policy network in a simple representation of a broad state. And in for this supervisor learning policy network, we have a P of A by S and P of sigma A by S. So here the P of A by S relates to the policy for taking actions as A given the state as S, and P of sigma A by S deals with the policy model by parameter sigma. So next slide deals with the supervised learning of the policy network. Here we propose a new policy called as a rollout policy, which uses a linear softmax classifier that is more straightforward. In this, each step takes 2 seconds to compute instead of 3 seconds in the supervised learning policy network. And this policy network is trained using the stochastic gradient ascent on a randomly generated state action pair, that is S comma A, where S uh, uh, deals with the state and A deals with the movement of actions to maximize the likelihood of the human. And the next slide deals with the reinforcement learning of the policy network. And this is the second stage of the training pipeline, which improves the policy network. We rapidly develop the reinforcement learning policy network using the policy gradient, reinforcing the deep learning. We begin using the new reinforcement learning policy network to play the games. In this reinforcement learning, the game outcome will be JT, where time step T is the one if we win at the end, or -1 if we lose. To make the reinforcement learning policy simpler to win, we change the model parameter. In reality, it is very identical to deep learning back propagation, with the exceptions that we utilize the game outcome just to determine which may be travel. So the next slide deals with the reinforcement learning of the value networks. So this is the last stage focus on the position evaluation, estimating a value function V of P of S that predicts the result of the games played from position S using the policy P for the both the players. We play the games against the each each other using the same reinforcement learning policy network to train the value network. The value network is similar to the policy network in a design, but instead of probability distribution, it produces a scalar value. By this, the game outcome Z we compute with the square error saying that MSE of the value function V of S. So the next slide will be continued by the my teammate Karthik with the continuation of the same reinforcement policy network uh, overview. Thank you.
Hello all, my name is Karthik and I'm going to continue from strength and accuracy of policy and value network. Using the policy network and comparison between value network and rollout network, use different policies. Here is the graph regarding strength and accuracy, policy and value of network. Moving to the next slide, Monte Carlo search tree with AlphaGo. The diagram below shows how to make a move into Monte Carlo search tree. There are 4 phases like A, B, C, and D. Moving to the next slide, evaluating the playing strength of AlphaGo. Looking at the outcomes of other Go programs, we can plainly see how dominant AlphaGo was in compared to other Go programs, winning the majority of games approximately 99% of the time. Down below is the graph for the evaluating playing strength of AlphaGo. Coming to the next slide, I would like to conclude by saying in this paper, we constructed a Go software that plays at the same level as the best human players, overcoming of a artificial intelligence grand problems. For the first time, we have built effective move selection and positive assessment function for Go using deep neural networks trained using a new combination of supervised and reinforced learning. We will develop a naval search technique that successfully integrates neutral network assessments with Monte Carlo simulations. Our software AlphaGo combines these components in a high-performance tree search engine at scale. From here, my teammate Nida will continue this.
Thank you. This is Neda. In this slide, I'm going to talk about mastering the game of Go without human knowledge. In the game of Go, AlphaGo became the first computer program to defeat a world champion. Deep neural networks were used in AlphaGo's tree search to analyze position and choose moves. These neural networks were developed by supervised learning from expert human moves in reinforcement learning from self-play. Supervised learning systems that are trained to evaluate the decision of human experts have made a significant progress toward artificial intelligence. Expert data sets are frequently expensive, unreliable, or simply unavailable. Even when credible data sets are available, the performance of systems trained in this manner may be limited. Reinforcement learning systems, on the other hand, are trained by their own experience, allowing them to operate in a domain where human expertise is limited and perhaps surpassing human capabilities. AlphaGo was the first program to reach superhuman level of Go performance. AlphaGo fan relied on 2 deep neural networks, a policy network that generates move probability and a value network that generates a position appraisal. The policy network was initially trained using supervised learning to effectively predict human expert moves, and then modified using policy gradient reinforcement learning. And also AlphaGo Zero is different from AlphaGo Fan and AlphaGo Lite. In this slide, I'm going to talk about reinforcement learning in AlphaGo Zero, which is the deep neural network F theta with parameter theta is used in the Noble method. The row board representation of the position and its history are fed into this neural network, which produces both moves probability and a value. AlphaGo 0 uses revolutionary reinforcement learning approach to train its neural network from self-play games. MCTS in AlphaGo 0 is going to be each simulation traverse the tree by picking the edge with the highest action value Q, as well as upper confidence bound U based on a prior probability P and visit count N. The neural network expands the leaf node and aces the related location S. A self-play reinforcement learning techniques is used to train the neural network, which employs MCTS to play each move. And to begin, the neural network is set up with random weight of theta 0. And empirical analysis of AlphaGo 0 training is going to be in order to train AlphaGo 0. It has been used our informant learning pipeline. The training began with purely random behavior and lasts for approximately 3 days without human involvement. It is a second neural network training to predict expert moves in the KGS server data set to compare the merits of self-play reinforcement learning to learning from human data. And this reached state-of-the-art prediction accuracy compared to previous studies. And utilizing either the convolutional network design from AlphaGo Lee or the residual network architecture from AlphaGo 0, in using either separate policy and value network as an AlphaGo Lee or integrated policy and value network as in AlphaGo 0. Using a fixed data set of self-play games generated by AlphaGo 0 after 72 hours of training, each network was trained to minimize the same loss function. The use of a residual network was more accurate and resulted in decreased error. Knowledge learned by AlphaGo 0 is going to be during its self-play training process, and AlphaGo 0 accurate and impressive degree of ghost expertise. They covered discovered not just basic part of human Go knowledge, but also non-standard strategy that were outside of the boundaries of traditional Go knowledge. Performance of AlphaGo 0 is going to be learning curve over 40 days with a large 40 block residual network, and also it's going to be last performance using a 40 block residual neural network. AlphaGo 0 was trained for 40 days. And final performance of AlphaGo 0 is using a reinforcement learning process on a second instance of AlphaGo 0. This time with a large neural network and for a longer period of time. Training began with absolutely random behavior and lasted around 40 days. So as a conclusion, the results show that a pure reinforcement learning strategy may be used to train the superhuman level, even in the most difficult domains, and which is possible to train to a superhuman level without using human example or supervision, and with only a understanding of a domain. And in additional, compared to training of the human expert data, a pure reinforcement learning strategy takes only a few additional hours to train and produces for superhuman performance. Thank you.
Yeah, recording. I think still it is in progress.
Yeah, I'm looking. I cannot find it.